So today I want to talk to you about potential energy and springs. So first let's discuss potential energy. An object has potential energy because of its configuration, its internal configuration, or its surroundings. Common examples of potential energy that are used in your textbook include wound up springs, stretched elastic bands, or objects placed at some height above the ground. You can think of potential energy as the energy related to the configuration of the system, and then the system is interacting with one another via forces that are internal to the system. I like to think of potential energy as stored energy, and the energy is stored in the arrangement of the system. So for example, for the stretched elastic band, it's stored in the bonds between the atoms, and when you stretch them, the bonds want to return. But they can't until you let go. So that energy is stored and it's just waiting. Or if you put an object like a drink up on a high shelf with half of it hanging off the edge, it's stored there in the height, in the distance between the drink and the ground, and it's just waiting to fall over and spill all over the floor. So stored energy. Now, we're going to talk specifically about two different kinds of potential energy today. And one of them is gravitational potential energy, and then the other one is potential energy stored in springs. So first, gravitational potential energy is the energy that an object has because it's some height above your reference point. The reference point can often be considered to be the ground, but the choice is somewhat arbitrary. Like if I'm standing on a balcony, okay, looking out over a street that's far below me, I could choose an origin of the floor of the balcony, or I could choose an origin of the ground far below me. So it just depends upon what problem I'm working as to what choice my origin is. Now what happens is when you lift something up, you have to do work, right, to fight the force of gravity. So you're lifting it up and you're adding energy to the book because of the lifting force. You're adding energy to that system. You can calculate the work that an external force would have to do to get to lift through this force of gravity, all right? And that would be equal to, as long as you lift it at constant speed so that there's no net acceleration, then the force that you'd have to apply to get it to travel at a constant velocity would be equal to mg. And then the height that you take it through, say that height is d, well then your work would be mg times d, okay? Or if you're talking about raising it to a height h, then it would be mgh. And so that's the amount of energy that you've put into the system by doing work, and that's what we define our gravitational potential energy as, mgh, or mgy, or mgd. Lots of times these things get used interchangeably. But anyway, the important thing to remember is that the height of the object above your reference point is what you want to put into that formula. So gravitational potential energy is the energy associated with an object at a given location above the surface of the Earth. Our formula for it will be mgy, m is mass, g is 9.8 meters per second squared, and y is the height in meters. That will give you units of joules, okay, for our energy, just like every other energy unit that we've had. This is a scalar and not a vector, so it only has a magnitude and not a direction. If you looked at the work done by gravity as the object was lifted through that height, then you would see that the work done by gravity would be minus mgh. And the minus sign is because the displacement h is opposite to the direction of the force of gravity, okay? So the work by gravity is the negative of the potential energy of gravity when you lift the object up. And this is actually a general statement. I made this for this one specific problem, but it's a general statement for potential energies and work. And that general statement is, the change in the potential energy associated with a particular force is equal to the negative of the work done by that force if the object is moved from one point to the second point. Okay? So work and potential energy, the equations are going to look very similar between the two, and they should be related by a minus sign. All right, let me do an example problem for you. This one is, what is the kinetic energy of a 1,500 kilogram car traveling at a speed of 30 meters per second, which is about 65 miles per hour? From what height would the car have to be dropped to have the same amount of kinetic energy just before impact? And what's the gravitational potential energy at that height? All right, so We learned about kinetic energy in the last lecture. Kinetic energy, the formula is 1/2 times the mass times the speed squared. So if you plug that into the formula for our car, you have 1/2 times 1,500 kilograms times 30 meters per second, and then you square that. And if you solve for that, you see that the car has 6.75 times 10 to the 5th joules of energy. Okay? So the kinetic energy depends on the speed. So what height will the car have to reach a speed of 30 meters per second at the ground? So if you drop it, right, how far would you have to drop it from in order for it to have a height of 30 meters per second? Because the question says from what height would the car have to be dropped to have the same amount of kinetic energy, okay? But since kinetic energy depends on the speed, then you have to use the kinematics equations to figure this out. So I'm going to use the one that doesn't involve time, okay? Vf squared, the final speed squared, is equal to the initial speed squared plus 2 times the acceleration times the change in the distance traveled, delta y in this case. Okay? I'm going to use that formula. So the final speed that the car has is 30 meters per second, just below impact. So I plug in for that, and that's squared. And we're going to assume that the car is just dropped, so it has no initial velocity. So the initial velocity is 0. And then plus 2 times the acceleration, which is the acceleration due to gravity, negative 9.8 meters per second squared, times delta y. And then what I do is I solve for delta y. When I solve for delta y, I get negative 45.9 meters. All right? So that's equal to, remember, a delta is the final minus the initial position. So since the final position is the ground, that would be y is equal to 0. So 0 minus 45.9 is equal to negative 45.9. So that means that the car was initially at a height of 45.9 meters in order to be dropped and reach 30 meters per second right before impact. All right? Now, if I take that height, 45.9 meters, and plug it into our formula for our potential energy, U is equal to mgh, or mgy, then you get 1,500 kilograms times 9.8 meters per second squared times 45.9 meters. You get 6.75 times 10 to the 5th joules. And I want to point out that that's the same number that we got for the kinetic energy of the car that was traveling at 30 meters per second. That's not an accident, okay? It's actually an example of the law of conservation of energy. So that says that energy is not created or destroyed, but simply converted from one form to another. So what would happen if you dropped a car from 45.9 meters is that all that potential energy that it had from its height, the mgh, that would be converted by the time it reached the ground into all kinetic energy, right? 1/2 mv squared. And since you're taking the reference point as the ground where height is 0, then it's all gone into kinetic energy by the time it gets to the ground. And so the total numbers, see, that is equal. It's the same, meaning it didn't lose energy. And of course, for this problem, we're neglecting air resistance, because air resistance would take some of the energy out of the system. But we're going to neglect that for now. So potential energy can become kinetic energy if the object's dropped. Potential energy is a property of a system as a whole, not just the object, because it depends on the external force, which is gravity, right? And like I said, it doesn't matter so much where you measure y from as long as you're consistent, okay? So as long as you choose your origin for your problem and stick with that origin, then you're going to be okay, okay? It turns out not to matter also if your potential energy mgh goes negative. So some of you, for example, if you had the problem where you were standing on the balcony, right, and you chose your reference point as the balcony floor and not the ground, but then you dropped a cup from, say, your shoulder height, which was above the balcony, but then it fell all the way down to the ground, and you chose the balcony as your reference point, you would have a negative gravitational potential energy. And that's all right, as long as you're consistent within your system and stick with that origin that you've chosen all the way through when you see the problem to its conclusion. Okay, so that's what I want to say about gravitational potential energy for now. Let me now move on to the other kind of potential energy that I want to discuss, which is the potential energy that can be stored in a spring. Okay? You can store potential energy in a spring by compressing it or by elongating it. So anytime you take a spring from its equilibrium position, then you're going to store some potential energy in there. In the graphic that I show on this slide, you show a spring at its equilibrium position, and then it gets pushed in by this ball. And then when the hand lets go, the spring rebounds out. And all that potential energy that was stored in the spring gets converted to kinetic energy of the ball. So the potential energy and a lot of things about springs can be described by Hooke's law. So Hooke was the physicist that originally came up with this equation, and he realized that the force that was exerted by the spring is always directed opposite to the displacement from equilibrium. So for example, in our previous example, we pushed inward, but the spring wanted to push outward back. So you displace it inward, and the force wants to return it outward to that equilibrium position. And lots of times this is called the restoring force because it wants to restore it to equilibrium. If you had your ball attached, or a ball or block attached to a spring so that it couldn't rebound and just fly off, then it would just oscillate back and forth about the equilibrium position. So here's a mass in a spring, and it's on a horizontal plane. The force exerted by the spring is F is equal to negative kx, okay? The force is negative. It's trying to push it in the negative direction. In other words, the force is going to be to the left, right? But the displacement is to the right. It's positive, okay? And Hooke's law says that the total net force is equal to this constant k, which is called the spring constant, times the displacement from equilibrium, x. Okay, so when x is positive, the spring is stretched, and F is negative. If you use the F is equal to kx equation, you can see that if x is the displacement from equilibrium, if it's at equilibrium, the force is 0. So you've got no force at the equilibrium position. And then when x is negative and the spring is compressed, the force is to the right, so it's positive. So that's why that minus sign is in Hooke's law, F is equal to negative kx, because you always want your force in the opposite direction to your displacement. If you're plotting this, force versus position, then you'll see you get this straight line, okay? You get a straight line, and it's got a negative slope. Now, what this means is that this force is not a constant force. So we learned how to calculate the work for a constant force, right? Then it's just the force times the displacement times the cosine of theta. But that's for constant forces. So how do you calculate the work for a force that varies, with your displacement? So what you do there is you can approximate your work by dividing the distance up into little tiny pieces and finding the work done during each of the pieces and then adding it up. And then what you'll see if you do this is that as the pieces become very narrow, the work is just the area under your force versus distance curve. All right? So that's a little bit of calculus that I did manage to sneak in on you, but it's also in your textbook, so don't blame the messenger. All right. So you calculate the work for a varying force by looking at the area under the force versus distance curve. So let's apply that to our spring curve, okay? So this is plotted on a positive slope, so it's the work done by an external force pulling the spring, okay? So this isn't the work of the spring, it's the work by the person pulling on the spring. If you're looking at the work of the force from external, you can use that to calculate your potential energy, all right? So here I've got F is equal to kx, and I'm plotting that on a straight line, okay? And then you can see that if you look from 0, which would be the equilibrium position, to some elongated position, which I'll call x final here in this graph, then you can see that the area under the curve is a triangle, okay? If you want to know what the area of a triangle is, the formula is 1/2 the base times the height. So here, the base is x final. That's the size of the base. And then the height of the triangle is k times x final. And then 1/2 x final times kx final gives you 1/2 k x final squared. And that's the general formula for the potential energy stored in a spring, 1/2 k x squared, where x is the displacement of the spring from its equilibrium position. So that's the potential energy formula for a spring, 1/2 kx squared. We call the potential energy associated with the spring often the elastic potential energy, okay? And remember that the force that the spring exerts is given by Hooke's law, F is equal to negative kx, and the potential energy of the system is 1/2 kx squared. So, if you look at a situation like this, where you take a block and you push it against the spring, compressing the spring, and then you let it go, what does that mean? What's happening? Okay, well, as soon as you compress your spring, you've given elastic potential energy to the system, okay? So if you're to look at what the total energy of the system is at that time, before the block is moving, it's all potential energy. Now you look at what's happening with the block at a later time. What's happening is that now the block has moved off the spring and it's sliding along if you're ignoring friction, okay? In that case, you've got kinetic energy, okay? So that's 1/2 mv squared. And yet again, you're going to see conservation of energy. All that potential energy that came from the compressing the spring went into kinetic energy of the block once it let go, all right? Conservation of energy. So, again, because it has to do with the displacement from equilibrium, if the spring is at equilibrium, if it's not deformed, then the potential energy is 0, okay? You can only store energy in a spring when it's stretched or compressed. You get the maximum potential energy when you've reached the maximum displacement of the spring, okay? And then 0 when it's at the equilibrium position. Unlike gravitational potential energy, elastic potential energy is always positive, because the spring constant is always a positive number, and x squared is always going to be a positive number. All right, let me do an example problem for you using springs. So we have a 10-centimeter long spring, and it's hanging from the ceiling. And then you hang a 2-kilogram mass on it, and that stretches your spring to a length of 15 centimeters. So what's the spring constant, K? And then, how long is the spring if instead of a 2-kilogram mass, you put a 3-kilogram mass on it and suspend it? So I have a little sketch here of the scenario. So here's the unstretched spring, and it's got a length of 10 centimeters or 0.1 meters. Then you hang the 2-kilogram mass on it, and that'll stretch the spring by some distance. Okay? That stretching of the spring is a total spring length of 15 centimeters or 0.15 meters, but we're really only interested in the delta x, the change from equilibrium. And of course that would be 5 centimeters, 15 minus 10, which gives you 5, or 0.05 meters. Okay? Now if you look at what's happening to the spring when the mass of 2 kilograms is hung on it, then you're not talking about an oscillating spring. You just hang the mass on it and it comes to equilibrium at some elongated position, right? Well, since it's not moving, there's no force on it, no net force. So that means that you've got the spring trying to pull the mass up and gravity trying to pull the mass down. So I've drawn the free body diagram for that here. I've got K delta X up and I've got mg down. To be consistent with this little drawing I found on the internet, I made the choice that X is up and down. It's an unconventional choice, but then I didn't have to draw my own picture and I could just steal one from the internet. So now that I've drawn my free body diagram, I'm going to find my spring constant K. So the sum of the forces in X is equal to 0 here, okay? And I had the spring force up, K delta X, and mg down, minus mg. So if I plug in for my numbers there, then I have K times 0.05 meters, that's the extension of my spring from equilibrium, minus 2 kilograms times 9.8 meters per second squared, and that's equal to 0. So if I take that simple equation and I solve for K, I get my spring constant, which is 392 newtons per meter. Now, how long would that same spring be if instead of 2-kilogram mass, I attached a 3-kilogram mass? Well, yet again, the sum of the forces in X would be equal to 0. So now I have K delta X minus mg. I know K now, so I can plug in 392 newtons per meter, but I don't know how long it is, so I leave it delta X. And then minus 3 kilograms times 9.8 meters per second squared. If I solve that equation, then I get delta X is equal to 0.075 meters. That's 7.5 centimeters. But for the total length of the spring, I would have 17.5 centimeters because I've got to add my original length of 10 centimeters to the 7.5 centimeters for a total elongation of 17.5 centimeters. All right, I hope that helps, and I'll see you in class.